Hi everyone, welcome back to the lecture today. So the topic of today is for the whole week will be regarding differential amplifier. So let's get to this. Differential amplifier will be the topic of discussion today. So previously we covered linear amplifier. That means you have one input, and in this case an input voltage, and you have one output. So you can see the how can I say this? The transmission, like the transmission of input to output, is linear. But now we will cover differential amplifier. So as you can see here, differential amplifier, we have an input V1 and then another input voltage V2. Then it will result to an output of VO. So another word is this type amplifier, differential amplifier. It's also called Diff-Amp, or you can call difference amplifier. The input in this differential amplifier is the input stage to virtually all of the operational amplifier or op-amp, and is probably the most widely used amplifier building block in analog integrated circuit. So as you can see, we have the output here, and usually the output would be equal to V1 minus V2. So basically it takes a difference between V1 and V2, then multiply it by the amplification factor or the voltage gain. So this one is called the open loop voltage gain. If you now consider the input, we have a definition called differential mode input voltage, and this is basically the difference between V1 and V2, so V1 minus V2. As you can see, your output will amplify that difference, so this is called differential mode input. Another input is the common mode input voltage, and this is defined by VCM, which is stand for common. Is the average of V1 and V2. The reason why we need to consider this is because that this VCM common mode input voltage can actually affect the output in non-ideal amplifier. So in here we have a basic BJT differential pair configuration, or you can call it a basic BJT difference amplifier. In this configuration here, Q1 and Q2 is assumed to be identical. Okay, so these two transistors are identical in every terms, like beta will be equal. All of the internal resistance and internal capacitance must be identical, and they must all be biased in forward active mode. Secondly, the source VB1 and the source VB2, they are considered as ideal source. That means your RS or the output resistance of the source is very small. Since both positive and negative bias voltages are used in this circuit, so the need for coupling capacitor CC and the voltage divider bias resistors at the input of Q1 or Q2 is not needed. If the input signal voltage VB1 and VB2 in here are both equal to 0, so if the input voltage VB1 and VB2 are both equal, then it results to an output of 0. But if they are both 0, VB1 and VB2, Q1 and Q2 are actually still biased in the active region by the current source IQ, and as you can see it here. The common emitter voltage VE would be on order of negative 0.7 volt. The circuit then is referred as a DC coupled differential amplifier. So differences in DC input voltage can be amplified. Although the difference amplifier contains two transistors, it is considered a single stage amplifier, so not multi-stage. The analysis will be shown later as we go through. So in here we have a basic BJT differential pair configuration, or you can call it a basic BJT difference amplifier. In this configuration here, Q1 and Q2 is assumed to be identical. Okay, so these two transistors are identical in every terms, like beta will be equal. All of the internal resistance and internal capacitance must be identical. And they must all be biased in forward active mode. Secondly, the source VB1 and the source VB2, they are considered as ideal source. That means your RS or the output resistance of the source is negligibly, it's very small. Since both positive and negative bias voltage are used in this circuit, so the need for coupling capacitor CC and the voltage divider bias resistors at the input of Q1 or Q2 is not needed. If the input signal voltage VB1 and VB2 in here are both equal to 0, so if the input voltage VB1 and VB2 are both equal, then it results to an output of 0. But if they are both 0, VB1 and VB2, Q1 and Q2 are actually still biased in the active region by the current source IQ, and as you can see in here, the common emitter voltage VE would be on order of negative 0.7 volt. The circuit then is referred as a DC coupled differential amplifier. So differences in DC input voltage can be amplified. Although the difference amplifier contains two transistors, it is considered a single stage amplifier, so not multi-stage. The analysis will be shown later as we go through. So as you can see, I put everything that I said before here. So if this voltage VB1 and VB2 equals 0, it will result to a VE of negative 0.7 because you have this VBE on equals 0.7 identical for the two transistors. So this circuit is referred as DC coupled differential amplifier. Differences in DC input voltage can be amplified. Okay, let's do a little bit of analysis. So if the base voltage are identical, so in the case of if the two base voltage are identical, you can actually connect the two base terminals together at a voltage VCM. So remember how we define VCM? VCM is equal to an average of the two input. So we can have VCM equal to VB1 plus VB2 divided by 2. So if you have the VB1 and VB2 is identical, they are VB1 equal VB2 equal VB is the same, and it's actually equal to VCM. So now you have this, right? Your VE will be, this VE will be VCM, which is the base voltage, minus VB on, which is 0.7 for most case. And since we have Q1 and Q2 are identical, in other words, that would be the beta for Q1 and beta for Q2 would be the same. In that case, you can see that if we have a current flowing through here, right? We see that the arrow point this way, but you can assume a negative current point the other way. So if we have these two branches are actually identical, you can see if you have a current flow, usually current will flow to the least resistance path. However, since these two branches are identical, then the current can be split evenly. So we can have IE1, which is the current on this branch, equal to IE2, which is the current on this branch, equal to IQ divided by 2, so half of IQ, because it's split evenly. Second, if the base current is negligibly small, in other words, if beta is large enough, you can actually assume the current, collector current, to be equal to emitter current. So imagine if you have like 200 for beta, then 200 over 201. It's not very different, so you can make that assumption. Then now you can have IC1 equal to ICE, and IC1 equal to IE1, IC2 equal to IE2. And that's why you have the collector current to be IQ over 2, and same for the other branch. Now you have those elements, right? You can actually calculate the output voltage at collector, okay, or the collector voltage for each transistor. Since they are symmetrical, so you can have VC1 will be equal to VC2, will be equal to V plus minus current multiplied by resistance, Ohm's law. Then you can have your collector voltage here, which is V plus minus half of IQ multiplied RC. So now if there is, so now to conclude, if you can see that VB1 and VB2 are equal, and if you also have Q1 and Q2 are two identical transistors, the current, so you see you have a current source, this current can split evenly on Q1 and Q2, and therefore the collector voltage will be also identical. Since there's no difference between the two collector voltage, so when you find the output, you can define your output as VC1 minus VC2. Therefore, the output will be 0 since these two voltages are the same. Now let's consider if base voltages are slightly different. So if I raise VBI, which is this voltage here, by a few millivolts, if I raise VB1 by a few millivolts and I decrease VB2 by the same amount for a few millivolts, and I define that few millivolts to be half of VD, then instead I can actually define the new VBI will be equal to plus half VD, and the new VB2 will be minus half VD. So in here and in here, as you see, this is the side split. Since the emitters are common, so they are connected together in here also, you can see that the BE voltage for the two transistors won't be equal. Precisely, VBE1 will be, which is this, VBE1 will be larger than VBE2 by the exact amount of VD. So this leads to the current, the emitter current, IQ1, to increase by a small amount of, an amount of delta I for the current, and likewise the current at the emitter current of Q2 will decrease by delta I. Therefore, we can have the collector current change also by the same amount, because we will assume that collector current is equal to emitter current if beta is very large, and hence base current is negligible. We have here. So now we have these two. You will be able to basically calculate the voltage at collector terminal, so the VC. So you have VC for both, then you can calculate the output of VC2 minus VC1. Then you can have the output voltage to be equal to 2 delta I multiplied by RC. So from here you can see that the output is no longer equal to 0. Let's go through one example together. So I have the basic differential pair BJT pair here. I hook it up to a 10 volt on the top and a negative 10 volt on the bottom. These two transistors Q1 and Q2 are identical. So the VBE on will be both 0.7 volt. Beta 1 and beta 2 will be set to be infinity, which means I just want it to be very large so that the base current is negligibly small. And finally, I can have my constant current source IQ to be 1 milliampere, and both collector resistance RC on both branch equal to 10k ohms. So first thing you can calculate is that so in common mode, that means VB1. The question is to find IC1 and VCE1. So I want you to find this current and the voltage between here and here. So VCE1, okay, which is also equal to IC2 and VCE2. For three different scenarios, when both base voltage equal to 0, when both base voltage equal to -1, and both base voltage equal to to -5, and both base voltage equal to +5. So now you know that I want to find the voltages, and if I want to find the parameter in common mode. And in common mode, I know that this current IQ is split equally on these two branches. So IE1 and IE2 will be equal. Therefore, IC1 and IC2 will be also equal to these two. And because it's split equally, it will be half of IQ, which is 0.5 milliampere. And as you can see, the equation is independent of VCM, so this value is same for all three VCM. Next, we can have VC1 will be equal to VC2, and how do you calculate that? You just bring this number minus 4 the voltage across this resistance, which is IC1 multiplied by RC. Okay, then how can I find VCE1, which is the voltage across here? So basically I would use VC1, then I would minus it for VE, and I know that VE will be equal to VCM minus 0.7, which is VBE on. So now I can plug this equation in here, and you can use Excel, MATLAB, or whatever you feel comfortable with. You can calculate your VCE based on VCM, right? So you have all of your number. Now I'm gonna go one extra step. If I plot if I plot IC1 against VCE1, I can observe a couple things. First thing I observe is that I can see, even though for different VCM, um, the collector current IC stay the same when the voltage across collector and emitter varies. So this actually make the variation that this actually occurs in variation in Q point, and as you can see in here. So this plot shows the variation in Q point. Next, as you can see in here, if BCM were about to increase over plus 5 volt, then Q1 and Q2 would be driven in saturation mode. So this demonstrates that there is a limited range of applied common mode voltage over which Q1 and Q2 will both remain in bias in the forward active region. I guess we can put a stop here, and next I will cover the DC transfer characteristic.
To sum up what we learned today, we learned a few things. We learned about differential amplifier that can operate in two different modes. Okay, the first mode is the common mode. In common mode, we have the two input equal to each other. Therefore, you would have an output. If you define output to be the difference between two collector voltages, you can have the output to be 0. The second mode is the differential mode. Okay, and in this mode you can actually do some math. So you can take the difference between two input, then you can amplify them up. Okay, and one last thing is that so these differential amplifier later on will be some building block for different type of operational amplifier or op-amp. So that's it for our lecture today. I will see you guys next time. Bye.